Hello, welcome back. In this video, we'll discuss the total internal reflection and construction of optical fiber. In the school days, you might have learnt about the Snell's law, which states that whenever a ray of light enters from a denser medium into a rarer medium, then the ray would bend away from the normal. In this arrangement, consider medium 1 with refractive index n1 and medium 2 with refractive index n2. And if a ray touches the interface separating n1 and n2 at point O, further let us say that n1 is greater than n2, means this ray is entering a rarer medium from a denser medium, that is a medium with a higher refractive index. n1 is having higher refractive index than n2. So n1 is greater than n2. As a result, the ray would bend away from the normal. This is the normal. With respect to the normal, we make the angular measurements in the case of refraction. So angle theta 1 is there, angle theta 2 is there for the refracted beam. The Snell's law states that n1 sin theta 1 is equal to n2 sin theta 2. Suppose you increase the angle of incidence, then you will see for one particular angle of incidence, the refracted beam follows the interface separating medium 1 and medium 2. And this particular angle of incidence is called as critical angle of incidence. And if you have the angle of incidence that is greater than theta c, which is the critical angle of incidence for this combination of dielectrics, under such conditions, the ray would reflect into the same medium. As a result, theta will be equal to theta prime. The phenomena of reflecting a ray into the same medium after interacting with an interface separating two dielectrics is called total internal reflection. The total internal reflection can be stated in this fashion. When a ray of light passes from a denser medium to a rarer medium, it bends away from the normal, and the phenomena in which light is totally reflected from a denser to rarer medium boundary is known as total internal reflection. In order to observe a total internal reflection, you do not need a reflecting coating. The interface or the plane that is separating these two dielectrics is sufficient enough to produce total internal reflection. The total internal reflection is used to develop a waveguide, namely optical waveguides. Suppose we have three slabs, slab 1 with refractive index n1 and slab 2 with refractive index n2, that is the bottom slab. Above this we have the slab 1 with refractive index n1, and above the slab 1 we have the slab 2, which means above and below the slab 1 we have slabs 2 which are having refractive index n2. And this arrangement, suppose we are placing in air. On this side we have the air for which the refractive index is equal to 1. If a ray of light touches the interface separating air and n1 material, which we call as core, then the ray would bend toward the normal because the core is having higher refractive index than air, and the bent ray would touch the interface separating n1 and n2 at this point. As a result, it undergoes total internal reflection, and a similar interface is present at this point also, which leads one more total internal reflection. As a result, light entering into the arrangement will be propagating from one end of the arrangement to the other end. If you take these three in the form of rectangular slabs, then you call such an arrangement as a planar waveguide. Suppose you take core in the form of a cylinder and the cladding also in the form of a cylinder, then what we have is an optical fiber. We have the core, all around that we have the cladding, over that we have the buffer. Core and cladding both are dielectrics. The buffering can be sort of a plastic material that gives the strength. So we have the core, could be a glass or a plastic material. Over that we have the cladding, it could be plastic or glass. Over that we have the buffering. Core diameter generally will be between 8 to 62.5 micrometers. Over that we have the cladding. The cladding diameter will be about 125 micrometers. And we have the buffer. The buffer will be about 250 to 900 micrometers. So that is the rough structure of an optical fiber. The cross section of an optical fiber looks like this. We have the core, generally this will be a glass, and cladding another glass, and over the cladding we have the silicon coating, and over the silicon coating we have the buffer jacket. This provides certain strength to the optical fiber. Over that we have the Kevlar coating, that is the strengthening material, and above the Kevlar coating we have the outer jacket, that is a polythene coating. The polythene coating will be a thin coating, and this is the structure of an optical fiber. In this video we have started our discussion with Snell's law. We have said that if you have two dielectrics separated by an interface, and if a ray touches the interface with an angle of incidence θ1 and refracts into the second dielectric with an angle of refraction θ2, then n1 sin θ1 is equal to n2 sin θ2, which is called the Snell's law. We have seen what happens if the angle of incidence is increased. Further, we have seen what is critical angle of incidence. We have seen the total internal reflection. We have seen how total internal reflection is used to construct the planar waveguides. And we have seen the detailed construction of an optical fiber. Thank you.